Hello again, beloved students. We are on random variable lesson number 3 of 4. This is our last kind of big one. The fourth one is a little bit of a follow-up on this one. And then we'll be through the curriculum. So this is binomials. We're going to talk a little bit about geometrics as well. So we'll get into that just a little bit at the end. But let's jump into it. So binomial setting, this may be something you've discussed in your higher algebra course, but a binomial setting has 4 big rules. And so you see the 4 rules here. Success or fail is a key that there's really 2 outcomes. There is no middle ground. And again, success is all relative. A success could be robbing a bank successfully, or it could be winning a hand in a card game, or it could be making a free throw. Or it could be missing a free throw. Again, it depends what we define as a success in that scenario. 2, you obviously see is bolded there, the fixed number of observations. This is really the key that makes this different from the geometrics that we're going to talk about, that there's a fixed number of observations. So this is that scenario where we're saying we shot 10 free throws. What is the probability that we make 5? Or what is the probability that we make 7 or less, or 8 or more, or whatever it happens to be? All of this is made possible by the idea that the observations are independent. So if we're talking anything with playing cards here, this would need to be with replacement. If you pull a card out, you have to put it back. If you don't put it back, then it's not a binomial or a geometric setting. That's a situation that you handle just in regular probability rules of taking away from your denominator. But in this case, we're putting them back, so there is replacement if we're ever selecting a card out of a deck or a name out of a hat or anything like that. And finally, the probability of a success is the same for each observation. These 2 sort of go hand in hand. Again, that with replacement part is what helps us keep that probability of a success the same. We do make some assumptions that, like in basketball, if you're shooting free throws, that there's not this, if you miss, that you're more likely to miss your next one or something like that on a mental element. And so we're just looking at in general the idea of things being independent. So as we get into this, here's our formula. This formula is on your formula sheet, and a couple things about it. You right here with this, this is n choose k is how we read that. Notice there is no fraction bar. It's not n divided by k. It's n choose k, which is just the idea that if we have, say, 5 trials and we have 2 successes, this is representing the number of different ways that success could be integrated into those 5 trials. For instance, we could have success, success, fail, fail, fail. Could have success, fail, success, fail, fail. It could be fail, success, success, fail, fail, and so on. Okay, and this is telling us how many versions of that there would be. And so that's 5 choose 2, which is a function on our calculator under math probability. But we will probably just deal with it in the sense of using our shortcut on our calculator. So you won't have to actually calculate that separately. But that is 5 choose 2, just how many different ways it can be ordered. The rest of that formula is the probability of a success raised to the number of successes. Okay, so in this example that I just put here, let's just say this is shooting a free throw and we're a 70% free throw shooter. Then in this situation, that would be, if we're a 70% free throw shooter, we would say here is 0.7 to 2 successes, as shown in the 5 choose 2. And then 1 minus p would mean that there's a 30% chance we're going to miss it. And there would be n minus k, or just how many fails would we have. So that would be the 3 fails there. All right. So that's our formula. Again, it's on the formula sheet. They do love it if you write it on the AP exam, but then you can use some calculator functions to get around it from there. Okay, so let's talk about the PDF. So there's two kind of modes of going about the binomial, and one of them is a PDF, and one of them is a CDF. So the PDF here is dealing with situations where we have an exact number of trials. So the way that I wrote down the formula on the last page was as a PDF where it was exactly 2 successes. So if we look at a situation here, PDF stands for probability distribution function, first of all, and that just means a probability distribution like you see here, and we have an exact number of successes. Okay, so what we could do here is we could fill out this table, and you can see the function here right below it, and here's what we would do. So on our calculator, under second vars, okay, if you go to second vars, which is distribution, second variables is distributions, hit the up arrow, and you want to go to, on my calculator, it's A, which is binomial PDF, okay, as you see right there. With binomial PDF, what you are looking at here now is binomial PDF, and depending on what version of a calculator you have, it will either ask you trials P and X value, or it will ask you to just put these three in like I have them written right here with the comma in between them. But in this situation, in our example, I noted that I have 4 trials. Okay, my probability of success is 0.6, and I'm going to look at actually 0, 1, 2, 3, and 4 successes. So all I'm going to do is I'm going to start out by putting a 0 in there. Okay. And this will tell me what my probability is of having exactly 0 successes on 4 trials with a 60% chance of a success, which hopefully you got 0.0256. Okay, now to fill out the rest of these, I could use my list to speed this up, or your calculator has something called second entry. And second entry is just second enter. So if you hit the second button and enter, it will bring up your previous formula, and then you can just arrow back and change the 0 to a 1. And that will hopefully give you 0.1536, and you can do second enter again and change the 1 to a 2, and you get 0.3456. Change the 2 to a 3, and you get again 0.3456. And then finally change the 3 to a 4, and that gives you 0.1296. Now, sorry to put you through all 5 of them, but the reason I want to do that is just to show that in the end, these do all add up to 1. So if you were to add all those up, you should get 1. The reason 2 and 3 ended up being the same is has to do with the choose element and then our exponents there. So that's the PDF in that situation. The CDF is the other side of this. So CDF stands for Cumulative Distribution Function, and that's something that we'll get to here shortly. But just a couple PDF examples here before we move on. So if you were selecting playing cards out of a deck with replacement, again, that with replacement is key here. So we had to say with replacement so that we followed the rules of independence and the probability not changing. What is the probability that you select exactly 5 total red cards out of 7 trials? Okay, so this would be a binomial. We are looking for the probability that x equals 5. Again, this is a capital X. It's a random variable. We had 7 trials. We're looking for 5 successes. The chances of selecting a red card out of a deck, well, 26 of the 52 cards are red, so that's just 0.5. And we want 5 of those. And then the chance of selecting a black card is also 0.5, and we'd have 2 of those. Okay, on our calculator, this would be binomial PDF, 7 trials, 0.5 chance of success, 5 successes. And for that, you would, again, second vars, go to the A, the binomial, we'd have 7 trials, a 50% chance of a success, and 5 successes, which would give us an approximate probability of 0.1641, or 16.41%. Second one, if you're guessing on every question of a 10-question multiple choice test with 4 options for each question, what is the probability that you get exactly 5 correctly, answer exactly 5 correctly? So this one, again, now it's probability that x equals 5. On a binomial formula here, we'd have binomial PDF. We have a 10-question test. Since there are 4 options, guessing on 4 options would be a 1 in 4 chance of guessing correctly, so that's 0.25, and the chance that we guess exactly 5 correctly. One time I had a student who finished a multiple choice test very quickly, and I used a binomial to figure out if they just guessed, what are the chances that they would have gotten as many right as they did. Unfortunately for them, the probability of it was like close to a 1 in a million, and so unfortunately it was a situation where it was relatively clear that this student had the answers in advance. So so there's a little tip and trick of how to use binomials to your advantage if a student is taking a multiple choice test. All right, so that's binomial there with chance of getting exactly 5 correct would be about 5.84 chance, assuming you guessed on all 10 questions of a 4 option multiple choice. CDF, as I mentioned earlier, CDF is the other side of this. CDF stands for cumulative distribution, and that just means that if we're looking at a table, we had the table a couple of slides ago that went from 0 to 4. PDF is looking at just one of these alone, whereas the CDF is looking at that all the way back to 0. So if I did a CDF of 3, it would be adding the 4 probabilities of 3, 2, 1, and 0. Now, naturally, you can see that I could have also done that by doing 1 minus a PDF at 4, by just getting rid of that one. And there are other times where we might want 3 or more. And if we want 3 or more, then we could do a CDF of 2 or less and do 1 minus that CDF of 2 or less, or you could do a PDF of 3 and 4. It's really about trying to find the most efficient way of going about it. But CDF, the cumulative, just means we're starting at 0 and working our way up. Okay, we never go the other way. If you want to go the other way, then it's a 1 minus, or it's a bunch of PDFs going up the other direction. So on our calculator here, the idea of selecting 5 or less red cards out of 7. Okay, so what we're really looking at is x being less than or equal to 5. And again, what you do then is you'd have 7 choose 0. And there'd be 0.5 to the 0, 0.5 to the 7, plus all the way up to 7 choose 5. Okay, going up by ones. And this would be look like this. Or on our CDF here, this would be binomial CDF, 7 trials, 50% chance of a success, 5 successes. Okay, so now you go back to second vars again. You probably noticed earlier there was another binomial option there. It's the CDF. We have 7 trials, a 50% chance of success, and we're looking for 5 successes. And that ends up being 0.9375. So chances are a pretty good chance that we would select 5 or less cards out of 7 that are red. Second example here quickly, it would be coupled with the complement rule, is in the probability of 5 or more out of 10. Okay, so this isn't 6 or more, but it actually is 5 or more. Okay, so you could answer this by getting the PDF of 5, 6, and 7. Okay, again, if we look at all of our options here, and this is what I do a lot of the time, is I'll just draw in a generic table just to know what I'm looking for. So this wants 5 or more. So what I'm looking for here is these 3. Okay, so I could PDF, PDF, and PDF, or I could CDF from here back. Okay, so it'd be doing the same thing as I did in the first example, but I'd put a 4 in there instead, and then do 1 minus that. Now, as you can imagine, the thing that can goof students up is whether you put the 4 or the 5 in the CDF here. But because we want it to be at least 5 or more, if we put the 5 in the CDF and do 1 minus, we'd subtract out the 5 instead of keeping it. So you do have to be just mindful of what you're getting rid of and what you're keeping when you're finding these probabilities. Just some other examples here. We're not going to go through all of these, but what is the probability to answer 5 or less questions correctly? So that'd be a CDF of 5 or less. At least 5 correctly, so you'd either PDF 5, 6, 7, 8, 9, and 10, or you do 1 minus a CDF of 4 correct or less. If you were guessing on every question, what is the probability that you'd answer between 3 and 5 correctly? Let's say inclusive here. So this one I'll just talk about quickly. Again, you'd have to be careful here. So we got all these different possibilities. Okay. And we want 3 to 5 correctly. So we'd want this one, and this one. So how do you do that? Well, you either PDF at 3, PDF at 4, and PDF at 5, or you could, sorry if you hear the error, I'm getting fanned by my 5-year-old. The other option here is I could CDF 5 or less, okay, and that would, and that would give me that all 5, 4, 3, 2, 1, and 0, and then I would subtract a CDF of 2 or less. Okay, so it'd be a CDF 10 0.255 minus, this is binomial, a binomial CDF of 10.25 and 2. Now this 2 is the key. A lot of times students would want to put 3 in there, but 3 again is part of what we want, so you'd have to subtract at the 2 there. So that's just more examples, or again, you could do a PDF of 3, a PDF of 4, and a PDF of 5. Sometimes it's just frustrating because the PDF could be 14 long, and then you're doing a lot of busy work there. So it's nice to have some idea of when you'd want to use a CDF. All right. Here are just some calculator screenshots. This would be if you had the older operating system, this is what it would look like. There's a PDF and a CDF that you can look at. There are mean and standard deviation formulas for the binomial. Okay, this is what it looks like. This is truly what it looks like on your formula sheet for the binomial section. Even has the word binomial, as you can see there in bold, so it's a good reminder for us. So there's the mean and the standard deviation. Note that these are mu and sigma. And again, whenever we have mu and sigma, hopefully one thing that makes you think about is a z, which does come down the road in our next lesson, that the sigma is the key there. Again, t's use s's, z's use sigmas. So these two line up with each other here. So we saw mean was standard deviation. You saw here was root. Quick calculation here. Again, for mean times p. So we've got 10 independent free throws. So mu here, or whatever you want to say, mu of x is n times p. So we've got 10, and then a probability of 70% of making a free throw. So we'd expect naturally to make 7 out of 10 free throws on average. Okay, might be 5, might be 9, might be 10, might be 3, but on average we're going to make 7. Okay, NP Q or NP1 minus P. Okay, so naturally the variance would just be taking the root off here, okay, if you wanted to. But our calculation here then would be 10 times 0.7 times 1 minus 0.7, or you could just write 0.3. And that would be approximately 10 times 0.7 times 0.3. You take the square root, would be approximately 1.45. So we'd be saying on average that we, out of 10 free throws, we're going to make 7 on average, give or take about kind of a general average of 1.45 free throws. So we think we'll make somewhere roughly between probably 5 and 9 most of the time. Again, that's based on how many standard deviations would want to go either direction. Typically, in a 95% confidence interval, you're going 2 standard deviations either direction. So if we were just to kind of push this forward through a confidence interval, we'd expect a margin of error of about 3 each direction. So that'd be between 4 and 10 free throws, which of course is a pretty wide range. That's what happens when you only have a sample size of 10. Again, don't worry about the confidence interval right now, but that's just the idea of connecting all these here, that a standard deviation is 1, 1 and -1 in each direction on a curve, and a confidence interval technically or typically goes 2 each direction. Okay, but for right now, just know how to calculate the mean and the standard deviation for a binomial. Geometrics, we'll go through this a little quicker. For a geometric, geometric is going to give you the probability that the first occurrence of a success happens on trial K. Okay, so what happens here is there is no fixed N. Okay, and no fixed N just means we're not shooting 10 free throws. We're just shooting until we make one, or we're not picking cards out of a deck. 7 cards. We're just picking until we get a red card. Okay. So the difference with the geometric is the trials are independent. We would still use replacement if we were picking, excuse me, if we were picking cards out of a deck. There's a success and a fail, just like a binomial. we just don't have that fixed number of trials anymore. We're just going until we have a success, which means all of our calculations are basically probability of a fail times 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 probability of a success, or however many times we fail before we succeed. So that is what this probability formula represents here, is just the idea of 1 minus p is the chance of a fail raised to the number of fails times the chance of a success. Because there's an indefinite number of trials here, there is one rule. So for instance, for the free throws, if we're a 70% free throw shooter, and the question was asking, what are the chances it will take us more than 5 shots to make a free throw? If it ever asks you something like that, where it could be 6, 7, 8, 9, 10, 11, 12, then that's actually, you can do as a little shortcut. That would be 1 minus p. So in this case, that's 1 minus p would be 0.3 here. Okay, because it's 1 minus 0.7. So sorry, picking up here mid-thought. Was deleting just a little portion. So we're back here. So the being more than 5 would be the chance of a fail, which here is the let's see, there we go. Chance of a fail, which is 0.3. To be more than 5 would mean that we failed 5 times. Now keep in mind, the other way you could do this is we don't have a 0 in a geometric, because you can't have 0 successes because you go until you have a success. So we could look at this in terms of a table again, just for ease of the picture here. And the chances of us having our first success on our first try would just be 0.7. Okay, that's the original. Now, second try would mean that we failed once and then had a success. Third try would mean we failed twice, so 0.3 times 0.3 and then 0.7. Fourth try would mean that we failed 3 times. Okay, fifth try would mean that we failed 4 times before we had a success. Again, it's just how many 0.3s do you have before we get to a 0.7. So what you could do for this question down here of more than 5 is you could actually figure out the probabilities for 1, 2, 3, 4, and 5, add those up, and then do 1 minus that, and you would get exactly what you got here, which would be about a 0.24% chance of it happening, that we'd take more than 5 free throws before we made one if we're a 70% free throw shooter. So you don't need the shortcut. It's okay if you don't think about it at all. You can always think about it in these terms up here if you want to. But the formula in general, again, is chance of a fail to the number of fails, and then times the chance of a success at the end. There'll always only be 1.7 in this example, because we only have 1 success and then we're done and we move on. Okay, so examples here. Fair 6-sided die, what is the probability of rolling a 6 for the first time on your 5th try? So this would just be probability that x equals 5. Again, capital X for the random variable. And again, for our table, we would be finding here just this spot on the table. And for the 5th try would mean we have 4 fails. So for a die, that would mean 5, 6 is a chance that we don't roll a 6, and that would happen 4 times. And then finally, we'd have a success. By your 5th try would be less than or equal to 5. Okay, so now this would be a little more busy work. So now this is where we would we'd have to find each one of these. Okay, and your calculator does have this as a shortcut on it as well. If you go second vars again, okay, and you'd in this case go to a geometric CDF. So this would have been a PDF up here, but this is a CDF, and it just asks you the probability, which in this case is 1/6, and then the x value, which in this case is 5. Okay, so this would be geometric CDF 1/6 5. This up here, sorry, I'm going backward, would have been geometric PDF 1/6 5. Okay. Now what we do there, again, we took 1/6 and then 5/6 times 1/6 and then 5/6 squared times 1/6 and then 5/6 to the third times 1/6 and so on. Okay, so the chance that we'd roll a 6 by our 5th try is about ends up being about, let's make this a little different color, about 0.5981 or 59.81%. Okay. After your fifth try would of course be 1 minus what we had there, so this would be sixth or greater. Okay, and so to get that, you could use the shortcut that we had. So this would be greater than 5. The shortcut we talked about on the last page would just be 5/6 to the fifth here. Or you could do 1 minus, and you do 1 minus everything that's 5 or less, which we actually just found in the second part there of the 0.5981. So you can go about it either way there, and that'd be fine. I'll leave it at that. Let's move forward here. Quickly, geometric does have a mean and a standard deviation as well. These are on your formula sheet again. This is exactly as it looks. And of course, you see geometric bolded there. Okay, the mean 1 over p is just on average how many tries will it take us to achieve our first success. And the standard deviation is, you can see, a little more complicated there, root of 1 minus p over p. So really the square root of a chance of a fail divided by the chance of a success. So as we look at this for the six-sided die, the mu being 1 over p would just be 1 over 1/6 here, which means on average, we would have our first success on our sixth try. Okay, so that just means if we kept rolling a die, on average, we'd get our first 6 on our sixth try. Standard deviation for x here is the root of 1 minus p over p, which in this case would be the root of a fail over the chance of a success. Okay, so you'd have this one, you just have to be a little more careful that you do order of operations properly on your calculator. But that would end up being a standard deviation of about 5.48. So on average, we'd expect to roll our first 6 on our sixth try, give or take about 5.48 tries there. So that's, again, a mu and a sigma, which could ultimately turn into a z if we follow certain rules properly from there. So there's your mean and standard deviation. Here's what it looks like on the calculator. Here's the geometric PDF, for instance. Again, I gave you some directions there, second vars and so forth. Show you how to get the PDF version of this. And then there's the CDF version of this. And I don't know why this got cut off, but 1 minus this would give you the probability of it taking more than 3 tries, is what that says there. So this CDF is going to give you, oh, sorry, not a 0 again. This CDF is giving you this one, and this one, because it's cumulative up from 1 for the geometric. And so if we wanted more than 3 tries, we could just do 1 minus that, and that would give us 4 on to forever. We'll leave it at that for now. Again, if this sparks any questions for you, please just make sure to ask them at some point here moving forward. Thank you. Bye-bye.